All right, how's everybody doing? No?
Yes.
Wow, there's so much negativity in the room. What's going on?
I will say that for the office hour. I have a lot of questions.
Okay. If you have a question you think is generally applicable to everybody here, then go ahead.
Right. So we don't need to copy the data sets to the function, right?
No.
In here, I will read the data set from Java
Yes.
and I will save that to the output to my function.
Yeah, that's fine.
Oh. Okay, yeah, I have one more question.
In fact, if you copy the data from my bucket to yours, that's wasting storage.
it took us like 10 minutes, but yeah, let's do it now. Oh yeah, what do you say? Try connecting the cluster. Um, there's a like, it's asking about the log file. And where we get that log file?
So when you connect to the cluster, you will have to start the Spark Connect server. When the Spark Connect server starts, it will give you the name of the file it's logging to. No, you have to start the Spark Connect server, which is different from connecting via SSH. You connect via SSH, and then after that, while you're SSH'd into EMR, you start the Spark Connect server. When you do that, it should tell you what file it's logging to. If you lose track of which file it's logging to, there is a specific directory in /var/log/Spark that holds the log files for Spark, and that should be in. Oh, crap. Hold on a second. Okay, so the Spark Connect server thing makes sense. So this log output is from the log file that we got from Spark Connect. So if you kind of scroll all the way up here, we're starting the Spark Connect server on this line. And right after that, it tells us the path of the log file right here.
Oh, I'm not getting that like such thing, but it's showing that it's already done. I'm not getting that name.
It's showing that it's already connected.
I'm getting the first line, but I'm
So we can talk about this specific thing during office hours. Okay. Are there any other general questions about the project?
I don't understand like the way that the redirects work. So for your example, you do so England makes the Great Britain and the Great Britain redirects to like in the data set, the page for Great Britain is where there was a redirect, right?
Yeah.
Okay. So then the page links where it's giving us the field from and then the target, like the field target thing.
Yeah.
Is there ever a case where we have a page that is directed to the redirected? Okay. And then also cases where the page, the source page itself is a redirect. linking to another page that's not.
Um, unless something is wrong with the actual data, you shouldn't really have a page that is a redirect page that links to another page, unless that page it's linking to is the page that it redirects to. It depends on how the page link um table structures itself that way. That's a good question. Like, does the page links table, if a page redirects to another page, does the directing page link to the directed page? That's an interesting question. I mean, we can answer that with a join. So that's a very answerable question, but I don't know off the top of my head. What I did do is if after accounting for redirects, because I account for redirects on both sides. So after I account for redirects, I eliminate the pages that link to themselves, basically. And like I said, when I look through your code and I look through your results, I'm not going to expect them to be exactly the same as mine because everyone's going to have a slightly different way of handling redirects because they're weird. Everyone's going to have a different way of handling the slightly crappy data that we have from Wikipedia that isn't completely logically consistent with its documentation. So, like for the link targets with the title, there are a bunch of things with null as the title, which doesn't make any sense. You should not have a page without a title because a lot of the time that's actually what's used to identify the page, but it has data in there like that anyway. And we also have redirect cycles in Wikipedia. We have pages that redirect to each other without like redirecting to an actual article or an actual page with any content in it. So that occurs more than a few times in the Wikipedia set. So your solution is going to depend on how you want to deal with all of that stuff. My solution is quite minimal in the sense that it doesn't take a lot of special care to deal with all of that crap. Because we're really just trying to go after the basics right now. Any other questions? Before we get started talking about aggregations. What happens if you don't use the storage level? So you're not going to be caching anything if you don't use the storage level. So let's say in this save function, you just took out this persistence in here. Every time you referred to this table, the table would have to be recomputed if it's not cached by Spark. Yes. So every time you recompute it, that takes time and it takes resources to compute that thing. So the easiest option is to usually persist it after you compute it, so you don't have to do it again every time you refer to it. Now, there are a lot of times when you will only ever use a table once. And when that happens, you can just kind of chain everything together in the same pipeline. Sometimes you have to make sure that pipeline isn't too long because when a pipeline is too long, Spark isn't always smart enough to deal with it. So there are times when I will have a pipeline with like 8 joins in a row and it just can't deal with that properly. So sometimes you'll have to kind of persist it anyway so that Spark doesn't get carried away with trying to optimize everything. Because it can get carried away. Okay. Wait. You can't be done. There's no way you're done. Yeah, you're not done. I didn't even start you. Okay. All right. So before we get started talking about aggregations, this is even more important and complicated than what we were talking about last time with joins. So almost everything I talk about in this lecture is probably going to be on the exam. because unlike joins where we have, the sort merge join and the shuffle hash join, we're almost always going to use the sort merge join. And so the join strategies and talking about them doesn't matter as much as talking about aggregation strategies. Those really matter. And using the wrong aggregation strategy has broken my code before. So we're going to talk about it. And there are only two that we're going to talk about. But it's important to know where to use what. So are there any questions on the join stuff before we get started with this? Okay. So we know that an aggregation is used to take many different rows and using some kind of function or criteria, reduce that information into a single row. And hence the name, an aggregation is also called a reduction or to reduce in certain frameworks. In the older API for Spark, aggregate was also called reduce. So group by, X column, and then aggregate was called reduce by key in the Spark RDD API. So we have these aggregations. Who has some examples of some aggregation functions from Spark that take a bunch of rows and calculate something based on that set of rows? What are some example aggregation functions? Sum. What else? Count. What else? Average or mean. What else? Yep. Min, max. What was that? Median's a lot harder. Median's a lot more complicated than any of these other ones. Because in a median, you have to sort the data, right? None of these others require sorting the data. And so we're going to put that in a separate category. So we're going to make a note of that, not a median. Yeah. Yeah, so that would require different aggregation techniques other than the ones that we're going to talk about today in order to calculate it, because they require the data to be sorted.
What if I just use the function in Spark? It knows to sort it first.
It would have to.
It will have to, but
Yeah. I wonder if Spark even has a median function. Does it? Because the median is a lot more complicated than the mean. Oh, it's Pandas data frame median. So it's not a Spark data frame. That's what it looks like. Let's just look at the list of aggregation functions to be sure. Because I would be very surprised. Okay. Returns the median of this column. Yeah. The median requires other special things. Because you're finding data that's in the middle of this distribution. And so in order to do that, you have to know what like the entire distribution looks like. So that's more complicated. And so you'd have to do other things to calculate the median. So we're not going to talk about median right now. What else? Mode. Anything else? There are some other interesting ones like count distinct. Like, let's say for a particular title of all of these pages, do we want to count the number of unique namespaces associated with that title? That's an example. So we use count distinct all the time. right? And you can use count distinct in SQL in the same way. The syntax looks something like this, right? These two things are equivalent. I actually want to do research on calculating the median because that is not simple. And there's also approximations for count distinct. And we're going to talk about why that is in a second. Are there any other aggregation types that we can think of? Yeah, we can calculate standard deviation. What else? Oh, I see what you're talking. You're talking about like a rank. So those are windowing functions, which are a little bit different because those require you to partition the data, but you can't stream them in the same way that you can stream data into these aggregation functions. Because when you're putting something in order, you have to have a global knowledge of how everything relates to everything else. You don't have to have any of that global knowledge within the key for these, right? Like if you're doing a sum, you don't need to know what the exact value of every previous value was. You just have to know the total of all the previous values. And then you add the current value to the total value, and then you move on. With a rank, you have to access everything all at once, do a sort, and then rank them. So that's different than what we're talking about here also. So we're not going to talk about median, partially because it's different from these other operations, and partially because in a distributed environment, I don't even know exactly how it works. I want to do research over a weekend, and I can get back to you about how medians work. So we're not going to talk about medians, and we're not going to talk about window functions. Is there anything else? Huh? We already have that. SONP? SONE. So. Huh? Oh, yeah. I see what you mean. That is, what is that? That is a Boolean OR aggregation, which Spark actually does have. There's a Boolean AND aggregation. There is also a bitwise and a bitwise OR. Anything else? Okay. So when we aggregate over a series of data, we know that the data is separated and partitioned by Spark into one or more partitions, and these partitions can live on different machines in the cluster. And so let's say we're trying to take the sum of a column, and the values of this column, might be separated into different partitions looking like this. So let's say we have 3 partitions in our data. And they look like this. So these partitions in the data are separated onto totally different machines. So we have to act like they're different lists. And every executor that's processing these partitions only has access to one of these lists. So if we wanted to calculate what the total value of all the values in this column are, and we had them on 3 different machines, how would we do it? Yes, that's what we do. We calculate the sub summation for every machine. And then once we have all the sub summations, we can add those partial results together to get a complete result. That's what we do for these kinds of aggregations. So we can add all of these up and have, a sum of the third list or the third partition. You can add these up and have a sum of the second partition, and we'll add these up and have a sum of the first partition. And then in order to get the final sum of everything, we would add these 3 partial results together to get the overall value for this aggregation. So we can see here that there's a bunch of different things going on, and there's states that's being managed across the cluster. So Spark actually allows you to define your own aggregate functions. And so it defines its aggregate functions, including the ones internally, using this interface, or at least an interface that's similar to it. So this interface, and we can create different instances of this interface, in Python, but unfortunately, PySpark doesn't actually allow you to create user-defined aggregate functions like you can in Java. So that was a decision I had to make when before I started teaching this class, is whether I would teach this in Java, in Scala, or in Python. And I know almost everybody here is already familiar with Python, so that's what I chose. As a trade-off, we're not actually able to do this in Python. So if you want to do this, you're going to have to use Scala or Java. So this isn't available in Python, but we can still kind of explore with the ideas here. So here's what you have. For every aggregation state, you start out just in this simple example where, we're not grouping by any column. So we're only doing an aggregation over the entire column. There's no group by. So we're starting off with this simple example of every partition starts off with one instance of the aggregation state. So let's define what the aggregation state looks like for the sum aggregation function. The values of this aggregation function, or the methods associated with this aggregation function, are you need to have a 0 value. In other words, before you start aggregating, what's the initial value? And what the initial value is going to differ depending on what your aggregation function is. So after you have your 0 value, you have your reduce method. Your reduce method takes the aggregation state and adds a single value to the aggregation state. So this is what happens when you update your aggregation state in a for loop. You just call the reduce method over and over and over to update the aggregation state. Make sense? Cool. Now the merge is what happens when you have the aggregation states from all the partitions and you need to combine them together to form a single result. That's what the merge function is. The merge function takes 2 aggregation states and combines them together into a single aggregation state. Now, after all the aggregation states are merged into one, we need to call the finish method, which takes the aggregation state and gives us the statistic or the result that we actually want. Does that make sense? So there are 4 things. We can ignore these 2 because these are literally just tell Spark how to convert the types from like Spark SQL types into Java/Scala types so the code can actually execute. There's something conceptual about these things. So we don't need to worry about these 2 things. So we have to define these 4 things in order to define an aggregation function. So let's do that for a sum. So we can create a class, sum aggregation. And so what we're going to do is we're going to say every time the constructor is called, so every time we create a new instance of a sum aggregation state, we're going to create the 0 value. So that's like the default value. That's what we start out with. So we're going to have self. It's just the object. And for this one, we only have, one element of the aggregation state, which is the total, right? So we're going to say self.total is equal to 0. And that's the only thing that we need to think about for the 0 value. Now, when we have reduce, we have a value that we're adding to the aggregation state. So how do we add this new value to the aggregation state? Huh? Yes. So we just add the value to our total. So now we need to merge. So we're going to merge this with, some, other sum aggregation. Other aggregation. So now what do we do? How does this merge work?
We need to add the total to the other aggregation and returning this somewhere, or we're gonna store it in a different.
We're gonna do this statefully. We're gonna do this statefully. So the way it works in here is it takes two instances of the aggregation state and combines them and returns a new instance.
So we would be creating a new object.
We don't necessarily need to create a new object. This depends very much on how this idea of an aggregation state and a merge is implemented. Spark chose to make it stateless and to return a new object. And I believe what happens is you actually might be able to edit this. But I don't remember. Because I don't think you actually have to create an entirely new aggregation state every time you do a merge, because that would be quite expensive. Because sometimes aggregation states hold a lot of data, and sometimes what you would want to do is between the two aggregation states, select which one is the largest and then merge one into the other. Does that make sense? And we'll see what this might look like in a second. So right now, what we're going to do.
Are you just gonna be total PBI?
Yeah. So I think
Some aggregation object or the other.
so. What I think we should do actually, we should return another one, but so this is going to be like a static method. This is not going to be an instance method. And then we're going to do multiple examples of how to define these aggregation states. It doesn't really matter for some because holding a single integer is pretty cheap, but it's going to matter for other types of aggregation state. So we're going to make this a static method and it's going to return a new instance, even if it might actually be pointing to the same object. Does that make sense? So we're going to say a.total plus equals b.total. That is not plus equals. That's plus equals. Like that. And now we have finish. So this is where we take the aggregation state and we need to give Spark the finished product so that it knows what the value of the result column from the aggregation function is going to be. So that would just be return what? Yep, self.total. So that's a sum aggregation. This makes sense to everybody? Okay. So let's set this up like this. So we have partitions. And we're going to have this as a partition. We're going to have this as a partition. And we're going to have this as a partition. All right. Now, in order to actually execute all of this, what we need to do is we would need to create, a single aggregation state. So this is the, global total, I guess. Some aggregation. And then we need to do for partition in partitions. We need to do like a partition aggregation. Actually, we need to do for value in partition. We would also need to create a partition aggregation object. Some aggregation. And we do partition aggregate dot reduce. And then we'll add the value in there. And then once all that is done, you'll take a global total and merge it with the existing total. Dot merge global total and the aggregation for that partition. And then when we're done, we produce the global total dot finish, and that gives us our total value, and that is 298 apparently. We can also check whether or not this is correct by looking at there we go. Huh?
Okay, so you said that because the partitions are involved in an aggregation state, but there has to be something above that too, that has an aggregation state.
That's what the global aggregation state is.
Right.
That could also be on the driver node. Because the aggregation state is pretty small most of the time. If the aggregation states are large, if the aggregation states are as large as the partitions, you have a problem. So the idea of the reduce is to take information about, an entire group of rows, or maybe all of the rows, and condense it down into a very small piece. These aggregation states are also used when you group by a key. It works a little differently in how the aggregation states are distributed, but the aggregation states work in a very similar way, and we'll get to that. And the aggregation strategies that I mentioned, the fact that there are two of them, hash aggregate and sort aggregate, are relevant for aggregations by key, not global aggregations over an entire column. So in Spark, that's the difference between using a group by and then a dot ag versus just using a dot ag. This example, we're just using a dot ag and we're aggregating over the entire column and we're not grouping by key. Got it? Okay. Does this part make sense to everybody? Cool. Okay. And actually, we can abstract this out even more if we wanted to, because we've defined this interface for an aggregation. So we can say the function is aggregate partitions, and we will have an ag state class, and we will also have partitions. So then what we can do is, because we have this common interface, we can actually just loop through the partitions and make this kind of abstract This is the stupid Python equivalent of using a polymorphic reference in generics. And so then we just return global total.finish. Whoa. So then we can say aggregate partitions. And we're going to do a sum aggregation on this list. Let's see if that works. Yay. Okay. So now we've abstracted all of this out. This piece of code has no idea it's using sum aggregation, so we can actually pass in the class as an argument because that's how generic programming works in other languages, but Python doesn't have that. So yay. And I'll put this on GitHub and everything. Question so far? Yeah. Huh? Okay. All right, let's do another one. Let's do another aggregation state. What do we want to do now? Let's do average. Feel like doing average. That's only slightly more complicated, but let's go. Okay. Average aggregation. So we want to initialize it. And when we initialize it in this function, we also decide, what our overall state looks like. So when we decide what our overall state looks like, what information do we need to calculate an average? We need the number of rows. What else do we need? Yeah, we need the total. So we'll have a total, and we will also have a number of rows. So then what we can do is, what does a reduce look like? What do we put in this reduce function? And this reduce function is adding a single value to the aggregation state. So what do we do? Yep. So self total and then self count. All right. Oh, yes, we do. All right. Now we need to merge these two things. How do we do that? Yep, we have the totals and we have the counts. Self total. Nope, not self, because this is a static method. Total, and then a dot count. B dot count. All right. Now, lastly, this is where this looks a little bit different from the above example. Is what does the finish method look like? So we have these two things. We have these two parts of the aggregation state. How do we actually give an average? Yes. Self.total divided by self.count. And so that should give us exactly what we need. And so now we don't actually have to really rewrite any code. We just replace the sum aggregation with the average aggregation. And nope, we didn't return it. Oops. 14.9. That is our average. And so we can also check math. I didn't actually execute that cell. Does anyone know what? Really? Does anyone know what the actual average function is in Python? Help. Oh, it's statistics.mean. It's not math.mean. Why not? There. That took way too long. Okay. So we got that right too. Yay. All right. Let's do one more. So this is going to be a bad example because we would practically never want to do this in real life. But let's do a count distinct. And so we know that count distinct is going to be a little bit weird just based on this. We have approximate count distinct, which uses an algorithm called hyperloglog. That is a lot more complicated than I'm willing to go to in this class, and because I haven't actually read the paper. And so hyperloglog is complicated. Count distinct is not. Because hyperloglog approximates the unique instances of a field. Count distinct gives you the exact amount. The only way to get an exact count is to just keep a list while removing duplicates, of course. So that's what we're going to do. So class count distinct aggregation. Okay. So what is our zero value going to look like? Yeah. So we're not gonna just be able to use a number because that would just count the number of rows. We want to eliminate the distinct rows. Do we actually have any duplicates in this partition? We do. 2 occurs twice. 1 also occurs twice. So we should have a different amount. Okay. So what would the zero state of this aggregation state look like? What are we going to start with? What's a data structure that we can use to find distinct elements? Set. Okay. Self dot, I'm just going to call them unique equals set. All right. So now we reduce. And we're going to add a value. And how do we add a value to this aggregation state? Yep. We add the value to the set. And that's all we got to do. Okay. So then we have to figure out, all right, so we have a bunch of aggregation states. How do we merge them together? What do we do? Huh? Yes. We can union 2 sets together. However, I want to do this a little bit more efficiently because there are going to be cases where one of the sets or one of the things that are getting merged together might be quite a bit larger than the other. And so what the Python union does is it will create an entirely new object and copy both into it. So instead, what I want to do is figure out among A and B which one is bigger and take the smaller one and add everything from the smaller one into the bigger one. So we don't have to do as many insertions. So what we're going to do is we're going to say by default, A is larger than B. So if the length of A's unique value set is smaller than the length of B's unique value set, we are just going to recursively call the same function, but with the arguments flipped. All right. So now we can make the assumption that A is at least larger than B, if not the same size. So now what we can do is we can take for value in unique. We're going to go A dot unique dot add value. And we're going to return A. Make sense, everybody? Good. Okay, now we have finish. What does that look like? You return the length of the unique set. Oh, there we go. All right, now we can just replace this. Well, you can replace this with a count distinct. Is that what I call it up here? Yep. All right. Now let's see what happens. Whoa. Count distinct aggregation object has no attribute add. What did we do? Oh, we didn't reference unique. Merge is not defined. Merge is not defined. Where do you get such ideas? Oh, it has to be that. Try that again. All right, so there are 14 unique values, and what I want to do is I want to actually check whether that's true or not. All right, good. Okay. So we got these three things, and so we'll notice that in this merge function, when you combine two aggregation states together, this merge function needs to have certain properties associated with it because this is a distributed system. There's no defined order to these partitions. And so you could potentially merge two aggregation states together from all these partitions in any order that you want. So part of the challenge of defining these interfaces is making sure that the merge function has these properties where no matter what order you merge a group of aggregation states together, you wind up with the same result. So that is the result of these merge functions having both the commutative property and the associative property. Who can tell me what the commutative property is? Yes. So if you flip the two arguments to an operator or a function, then the result of the function will remain the same. What is an associative operation? Yes. So an associative operation can be grouped any way that they need to be, any way that you want them to be grouped, with parentheses without changing the order that will not change the result. So it's basically saying we're going to use plus as the operator. A plus B plus C is equal to A plus B plus C. So that's associativity. Commutativity is A plus B is equal to B plus A. So in this merge function, we know that for the sum, the merge function is both commutative and associative because it's just adding the total. So you can add this total every which way imaginable, and you will still wind up with the same result. And it's the same thing with the average aggregation, but you're adding just two numbers instead of one, and those numbers are independently managed. So it's the same thing. For the count distinct aggregation, The same thing applies. If you take the union of a group of sets, it doesn't matter the order that you union all these two sets in, as long as you union them all together, you'll get the same set at the end, right? So all of these merge functions have this property. Does this make sense to everybody? Cool.
So it determines what you can fit in the index versus what you can fit in the index. Because you have to make sure everything in the merge is clearly associated, so you have to be the guiding. And if you're going to be standard deviation, it forces you to put and then the rest of it into the things.
Yeah, because let's say we did the division before we did the finish. You're not taking the average of all the numbers properly because you would be kind of assuming that every partition had the same number of rows, which you can't. You have to make assumptions about the partitions in order to make this correct, which it's not. So you have to carry the entire aggregation state all the way to the end up until you have one aggregation state. Make sense?
About the reduce, does this refer to the map reduce? Or is this
Basically, so reduce means a lot of different things because it's been assigned to it's an overloaded term. So reduce is an actual function in Python, just vanilla regular Python, where you can take a list and submit a function, and that function defines how to combine two different elements of that list into one. And it'll keep reducing down to one element of the list. We actually went over this example in class when we were talking about functional programming. So that's reduce according to Python. Reduce, according to Spark, is taking an aggregation state and absorbing another value. And reduce for MapReduce is taking a key, taking all the rows associated with that key, and then producing X number of rows. So MapReduce is kind of a lower level construct when it comes to these sorts of things. So in MapReduce, I don't think you even necessarily have to produce a single row as a result. But I'm not sure about that. I haven't programmed MapReduce for like 5 years. And the only time I've ever done it is actually in an earlier version of this class. All my professional experiences in Spark. Questions so far? This is the API that Spark uses to define aggregations. And so we can define, these kinds of aggregations in any language, and it's basically the same. And this is, I haven't actually looked at Spark source code, but I'm willing to bet it looks something like this, where you just pass in the class or the definition of whatever aggregation you want, and it has the same generic code that deals with all aggregations. Cool, right? All right.
is that a certain aggregation strategy?
That is not the aggregation strategy. So the aggregation strategy has to deal with how the data is organized and how these aggregation states are created and managed. And that's different from how the aggregation states actually process the data. So those are two different things. And that's what we're going to talk about next. So all of this is easy to understand when we're only dealing with a few aggregation states. Because right now, we only have one aggregation state per partition. That's not very much because, when I'm writing code in Spark for like our identity pipeline account, we have 12 billion rows in there somewhere, and we have 4,000 partitions. 4,000 is a much smaller number than 4 billion. You can send 4,000 aggregation states to the driver node. It can handle that just fine. You can handle that many rows on one machine, it doesn't matter. But let's say you want to aggregate by key. And when you aggregate by key, you still have all the values of these columns, but you have an aggregation state for every key now. Does that make sense? So let's say we had a table with 2 columns where, we're looking at shirts, and these shirts have two different attributes. One attribute of the shirt is the color. The other attribute of the shirt is the price. So let's say we want to find what's the average price of every shirt for a particular color. So we would group by the color and do an average over the price, right? That means every color has its own aggregation state, right? Okay. So the aggregation strategies define how these aggregation states are managed. And there are two aggregation strategies that we're going to talk about. They're called hash aggregate and they're called sort aggregate. And which one you want really depends mainly on the distribution of your keys. As in, do you have a large number of unique keys or do you have a small number of unique keys? And that's really important when you're trying to decide which one to use. Okay, so let's try and write the code for a hash aggregate. Right now, we're going to keep using this example, except I'm going to change the aggregation key to just be whether the number is even or odd. So the aggregation key is literally just going to be a Boolean. Is the number even or is the number odd? And so what I'm going to do here is, hang on, I'm doing this ad hoc. Give me a second. So partitions. Um, so if it's an even number, we're going to say true. Okay, so that let's see if this actually gives us what we want. Oh, wait, no, we still need the actual element in here. All right, this is a pretty good toy example. Okay, so we're going to write another aggregate partitions, but we're also aggregating by key. So right now, we need a few arguments to this hash aggregation. So we're going to hash aggregate the partitions. And we're going to still need an aggregation state class. That hasn't changed. We're still going to need the partitions. We're also going to need a way to access the aggregation key because these are just rows. So we're going to say, this is just going to be a function, a generic function that you pass in. So aggregation key, and that's going to be a function that we pass in. And the other is going to be the aggregation column. Right. So these are arguments. Make sense to everybody? So when we do an aggregate by key, we do a type of aggregation. So that's the aggregation function. And that is defined by the class. We have data that we're aggregating over. Those are the partitions. We have the key that we're aggregating by. So this is the group by part of the statement. And then we have the aggregation column, which is the argument to the aggregation function that we would use. Those four parts make sense? No? Okay. All right. So what we're going to do first is we're going to define a, what should we do? This is going to be slightly altered from how it's actually done. What we need to do actually is we need to combine. We don't have that time for this. I took too long talking about this. We're going to have to continue this next time, but we're going to start right now. So right now, we're going to need a dictionary from full of aggregations from the values of the aggregation key to the aggregation state for every key. So what we're going to do first is we're going to loop through the partitions. And then we're just going to have, actually, what we're going to do is we're going to use a default dictionary. So does anyone know what a default dict is? Okay, so a default dict is a dictionary where you can set a default value for any key that doesn't exist. So if you try and access a key and the key isn't there, it will create a value for the key using a function that you define. So we're going to define the aggregations as a default dictionary. And so let's say we're adding in a value of the aggregation key for the first time. So when we do that, we're going to create the aggregation state. So it's just going to be lambda, and the function has no arguments, and we're just going to initialize it. We're just going to initialize the aggregation state, and we're going to return that initialized aggregation state. And because this is an object, once that object is returned, it's going to also have a reference from within the dictionary, and so we'll be able to edit it. Make sense? Good. Okay, so now we're going to say for value in partition, we are going to take the key and we're going to retrieve, so we're going to retrieve the aggregation key from the row. And then what we're going to do is we're going to get the state from our list of aggregation states. And then what we're going to do is we're going to say state.reduce. So we're adding in one of our values, and that value is going to be the aggregation column of the row. I should actually replace this with row to make it less confusing. All right, makes sense so far? Okay. So now what we're doing, that's going to be a function that returns the aggregation key for the row. So it takes the entire row and gets the aggregation key. Okay. So then all we should really need to do is we should be able to just return the aggregations yeah. So we're going to return the aggregation key. And then we're also going to return the aggregation value dot finish for every key and every aggregation state in our list of aggregation states. Okay, so now we want to actually call this hash aggregation of partitions. So we pass in, let's just say we want to do the sum. And we have our key partitions. And what this is going to be, I'll separate it onto different lines so you can see. All right, so this is going to be a function that takes a row, and every row is just a tuple here. So the aggregation key is the first element of this tuple. So it's going to be whether or not that value is true or false. And then the aggregation column, the argument to the aggregation function is going to be the second value of these tuples. So it's going to be the actual number. Okay, so let's see what happens. All right. Oh, yep, that's right. Cannot unpack a non-iterable Boolean object. Oh, that's right. We need, okay, there we go. So now we just found the sum of the values for all the even numbers versus all the odd numbers. So if you go and look back at the original, we can say that, okay, these two total to 298, which is the same total that we got earlier when we were adding everything else together. So let's do some more testing and see whether or not we got this right. So we're going to say the sum of the filter, and I forget what order these arguments go in because I always forget what order the arguments go in. Is the function first? We're going to say x mod 2 is equal to 0. Function object is not iterable, so that means I flip them. All right, 2, 3. And so now we can check the inverse, 68. Okay, so we got this logic right now. So what a hash aggregation does is it will take every key, and for every key, create the aggregation state. Now, I'm cheating right now. And the reason I'm cheating right now is because I have a global dictionary of aggregation states, and regardless of what partition it's in, I'm adding it to that aggregation state. So that's cheating. We have to stop doing it. We have to do something else. So we have to aggregate the aggregation states. So we can create a separate class hash aggregate aggregations. And this is just going to add a bunch of aggregation states together. And so what we would be doing is we only have like 5 minutes left. Yeah, that's enough time. So anyway, the reason this is cheating is because right now I am basically pretending that all of these partitions are on the same machine and they all have permission to write to this global dictionary. That's cheating. That is not how distributed systems actually work. So we're doing this incrementally. So this is not how they work. And we might have to stop before the entire thing is done. So for every partition, we're going to have one of these aggregations default dictionary. And then we're going to merge all of these dictionaries together and merge all of their aggregation states together at the very end.
Or would you have like a global aggregation state per partition? Not per partition, per machine. To put those partitions together before you go back.
So how it works is for every aggregation key, we're creating this aggregation state per partition. So in this example, the value true has an aggregation state and the value false has an aggregation state. And we do this per partition. And so after we do it per partition, we actually do a shuffle. So after we do the aggregations within the partitions, we then send the aggregation states to other nodes, depending on what the aggregation key is. Because, true and false both have aggregation states on every partition. So whenever we run it per partition, we have 2 aggregation states per partition. We have true and false for the first partition, and those have their values. We have true and false for the second partition, they have their values. And then we have true and false for the third partition, and those have their values. So once that part is done, once the first pass of it is done, we need to take every aggregation state under the true key and send it to the same machine. And so we're going to say every aggregation state with the key value of true gets sent to machine 1, and every aggregation state with the key value of false gets sent to a different machine. And so once the aggregation states all come in, we can merge them in as they come in. So we merge them again and again and again until we only have one aggregation state per key. Good? Okay. So we have like 5 more minutes. We can stop here and continue this conversation next time because I want to develop this to the point where we're not really cheating anymore. We're just pretending it's not distributed. Because this is a lot simpler than showing you what actually goes on in the Spark code, which is not even readable. It's not readable because of how abstracted it is and because it's Scala, which is not great. So we'll just leave it here. And just remember, we're cheating right now. This is not how it works. Okay, so if there aren't any more questions on this, then we're done. And I will see you all on Tuesday. Sweet.